Today we're going to be discussing static stress and static failure analysis. Now, as a prerequisite to this material, you will need to understand basic stress analysis, such as how does loading cause stress? How does stress concentrators work? And then how do we calculate principal stresses? Each one of these is going to be an important factor for us. And we didn't give a lot of discussion to the stress concentrators, but your textbook does. So I would encourage you to look over some of those examples, look at the material there. Textbook will give a lot of tables of values. Use this as a stress value increase. And it does have a lot of material in this. I'm kind of rushing through some of these lectures, trying to make sure that we get through the material we need to in the time that we get it done. So just bear with me here. So when we're talking about static failure, the basic principle behind static failure is that we think that failure will occur when the energy between molecules inside of a material becomes so large that the bond itself can't handle it. So it actually causes the bond to rupture. Now some materials, some self-healing materials, have the ability to redevelop intermolecular bonds. In some ways they do it by having the material behave like a fluid. That's one way of doing it. But for the most part, for most materials that we're dealing with, if those intermolecular bonds break, they do not reform. And this leads to kind of an understanding of where we're talking about with fracture mechanics. Now, fracture mechanics is a graduate level course. The idea behind fracture mechanics, it involves some really intense stress analysis and stress theory, which I don't want to get into in this class, but I do enjoy talking about it. I do think it's a valuable topic. It's just not an undergraduate topic. But there's a little bit of discussion provided in the book, and I do think that there's some concepts that are helpful to understand when understanding what causes static failure. So that's where we're going to take this approach for fracture mechanics. The basic idea behind fracture mechanics is if we were to treat every material as if it was an ideal material, nothing would ever fail until you get uniformly the energy for every one of those bonds is exceeded by the total energy put into the system. But at that point, we would be assuming that materials could be able to handle magnitudes of order large forces than what they actually can. So unfortunately, treating materials as if they're ideal materials does not work for fracture mechanics analysis. But what they did find was that, let's assume in every material there is a microscopic crack or hole. Okay, I was taught the term crack and lots of crack propagation and all of that. I have also heard the term hole, so just different ways of describing the same thing. Now, we're going to assume that in every material there's a crack. We talked about in this class the annealing process, getting boundary layers to flow again, causing it redevelops a lot of the intermolecular bonds when you heat up a material and let it cool down. We talked about quenching. We talked about cold working, which creates dislocations inside of the material, which is actually breaking of intermolecular bonds themselves and forming I don't know what the word I'm thinking. I'm just not going to finish that sentence. But we have the ability then to be able to look at each of these factors and say, okay, if a crack exists, this may be due to the inclusion of a material. Let's say you get a little bit of dust inside of it while you're forming a metal. It may be due to just simply how the material cooled down. There may have been a void. There may be an air bubble. There may be, even just a couple of molecules of air is enough to create a microscopic crack. We don't need a whole lot in there. And it's hard to have a pure material that has absolutely no impurities, is perfectly latticed, because interestingly enough, it would take a lot of energy to do that. And that, yeah, we haven't seen examples of that. Although a lot of material scientists will try to get there, but that's on them. I don't play in that realm. So if we assume that every material is going to have a microscopic crack, the thing is, we expect that to happen. We expect that to be behavior of a real material. And so we're going to go ahead and draw our material, and then in the middle we're going to have some kind of a microscopic crack or hole. Now, in this system, if I apply a load in this direction, a tensile load, what's going to happen is you're not carrying any of that tensile load on this piece of the hole. Okay, you're going to have some stress concentrators here and here because of how large it is, but ultimately right in the middle, this part here does not carry any load. So what we have is that the load ends up having to kind of go around this system, and it leads to stress concentration here, here, and there. And that stress is substantial. Now, as we pull on this, what's going to happen is that because of the stress concentration right here, if I go ahead and bring this piece out, because of the stress concentration here, when I apply a load in this direction, it's actually going to pull this way, it's going to pull this way, and it is going to want to pull that crack apart. It's going to want to grow and propagate that hole. And so what we see is that if we load this material enough, that crack is going to expand, and if we continue to pull on it, well, it's just based off of how much energy can be held at this portion of the crack right here. A material that may have a lot of cracks or some very large cracks in it is not going to be able to handle a lot of load. Whereas materials with really, really tiny cracks, that's actually going to be it's going to be really close to the total strength of the actual material out here. Okay. But what we see and what we're seeing out of each of these is that as we continue to pull, as we continue to load, as this cross section is loaded, we increase the bond energy at every one of the molecules in here, between every one of the molecules. And as we increase the bond energy, we will occasionally exceed the bond energy of this. Now, it may round out as it expands, which may mean that, okay, initially it can't handle a little bit of load, but then the crack propagates a little bit, but now it's rounder, so it can handle a lot more load. We may see something like that. But ultimately, this crack continues to propagate as we continue to increase the load until what happens is, if we're looking at the whole specimen here, as I continue to pull this apart, eventually this crack will propagate through the entire material. Okay? And when that happens, it's called what's known as fracture, okay, or failure or rupture. All three of those terms basically mean the same thing. It's ripping apart those intermolecular bonds, and the crack is propagating through the entire cross section of the material. Okay, and this is our assumption of basic failure. This is also our assumption of basic plastic deformation, because in each of those cases, if I were to stretch this out and then leave it, well, these holes, these microscopic cracks that are inside of our material are going to stretch. And that stretching, it does make them a little bit stiffer because it streamlines the whole location. It does change the energy in the area and how it carries load. It does change the intermolecular behavior. And so we see some plastic deformation when we pull on it too far. We are going to see some strain hardening, which is something you probably should have learned in mechanics and materials. But we are going to see some kind of a strain hardening, and when that happens, yeah, it's going to take more load in order to plastically deform it again. But that's basically all boils down to our fundamental understanding of fracture mechanics. So what does this have to do with anything? Well, excuse me. There's a couple of different pieces that we have to consider as we look at the fracture mechanics model of failure. Now our goal is we want to be able to identify how much load a system can handle before it fails. And in order for us to do that, we again have to understand stresses, we have to understand concentrators, and then we have to be able to calculate the principal stresses. Okay? All three of those work collaboratively to come up with our idea of how we can frame our understanding of failure. So we're going to take these concepts and we're going to plug them in. On this side of the board, I'm going to break this up into two pieces. Some materials we are finding do not plastically deform. Those materials fail, and it's called a brittle failure. Okay, so our biggest classification and differentiator in failure, static failure, is going to be, we're going to have two categories. We're going to have ductile failure, which involves plastic deformation, and then we're going to have brittle failure, which involves fracture. Now, the thing about ductile failure, when we're going to discuss ductile failure, is the condition that must be true is the material must be able to absorb energy through plastic deformation. And in ductile failure, I'm running out of room. In ductile failure, this will rely on SY, which is our yield strength. Okay? When we're talking about ultimate strength or ultimate rupture, we are talking about brittle failure. In ductile failure, all of the mechanisms we have in the book that we're going to be discussing in this class, all of them have to do with, we do not want plastic deformation to occur. Okay, if you can imagine, you know, if the piston in your engine, suddenly that piston expands, well, it's going to freeze, and it's going to cause your engine to seize, and a lot of bad things happen in there. You don't want that expansion, you don't want that plastic deformation of that piston head because it disrupts the entire flow of your system. So here we're going to rely on SY. That's going to be a differentiator for ductile failure. All of our ductile failure methods rely on the yield strength. They do not rely on ultimate strength. And in evaluating ductile failure, we're looking at how close to the elastic limit we are at critical points. And that's basically the whole evaluation. It's relatively straightforward, but that doesn't mean that scientists and material scientists agree on this topic. The unfortunate nature is that there's several different things that have been noted during failure that different groups of people will take on, and some of them apply to different materials differently. It does take a lot of testing to figure this out, and if I'm going to be honest, material testing overrules everything we're learning in this. This is just, it's an attempt to not have to do as much material testing, to understand what's going on, so that when we do material testing, in order to verify our results, we can be a little bit more deliberate about that. So we're going to talk about three different ductile failure theories first, and then we're going to talk about three different brittle failure theories, and that's going to be this lecture. So to start out, we've got maximum shear stress. Theory, which is abbreviated as MSS. Okay, key principle, what we're dealing with here is we've noticed that when something plastically deforms, it usually deforms at 45-degree angles. Now, the significance of 45-degree angles when we're applying a plane stress is that is the orientation of our maximum shear stress. Regardless of what the stress concentrations are, 45 degrees from the principal stress is going to be your maximum shear stress. So we are seeing that a lot of the failure planes occur 45 degrees relative to flat. So that would look something like that jagged edge that I had drawn over here, where we're seeing portions of this material kind of elongating, stretching. It's evidence of a shear stress that's present. Now the basic idea behind this one is that since we're going to experience shear failure, then our failure criteria is going to be related to shear stress. Now there's a derivation in the book. I'm not huge on drawing out derivations because I do think that you can go find that. But we end up with one basic equation that we're going to be used to determine static failure. And that is sigma 1 minus sigma 3 is equal to Sy over n. Okay? This is the equation that we use. Now, we already talked about how to determine sigma 1, sigma 3. I'm not going to go back over that. That is a topic for a previous class. Sy is a material property. This is going to be something that you either look up in a table or you get it specifically from the material manufacturer that will tell you what the yield strength is of that material. And this n value is the factor of safety. As I said over here, we want to be able to determine how close we are to the elastic limit. Well, our factor of safety is how close we are. When n equals 1, we expect failure to occur. Okay, now this ends up being a statistical property because of the way that fracture mechanics works and because of the variability in materials. We aren't going to see every material fail at an exactly specific load. But what we will see is that a lot of materials that are made at the same time and the same processes come from the same material batch. They do tend to fail similarly. So having a billet from one batch of material where you may have a whole bunch of bolts or something, we can determine what that static testing value is, and then we can apply that to the material, and then from there we can make our calculations. When n equals 1, we would probably expect more than 50% of our samples to fail. That's basically what we're saying. It's the tipping point. When n is greater than 1, we expect that failure will not occur. Now in some systems you're going to design with a safety factor that may be 1.15, where we try to be really close to that 1 value without getting all the way to 1. Whereas in some safety factors you're going to be dealing with a factor of safety that may be 10, 15, or 20. And some of that has to do with a little bit of uncertainty. We kind of roll the uncertainty into the factor of safety. Larger factor of safety, we don't have to be as certain about how the stress conditions are being applied. And it does give us a more conservative estimate too when we're trying to determine what we can do to determine whether or not failure is going to occur. So conversely, if n is less than 1, we also expect failure to occur. It's just n is less than 1, the severity becomes bigger because you're almost guaranteed failure is going to occur. Like I said here, about 50% of samples would fail. The lower you get, the more and more probability you're going to have samples failing. So that is this equation. Now this is the easiest equation to use because you only have one. This is it. And there's no real variability. The problem is that maximum shear stress theory is very conservative. What we were finding is that even though the n equals 1 value, we're supposed to be expecting failure to occur, we were actually seeing that closer to about 80 to 90% of samples were still working at n equals 1, and even values of n slightly less than 1. We were seeing a lot of these samples were still functional, we're actually still good. So it says, well, we're being a little conservative in how we're calculating our n value using maximum shear stress. Now it's quick, fast, easy. You need to know why we use max shear stress theory. Some of it's because of the materials it just applies better, but most of it's going to be quick, fast, conservative. It's going to give us an answer that'll allow us to proceed with design calculations. Doesn't require a lot of work, can be done really quickly, assuming we know what the principal stresses are. Okay? If we want a more accurate stress valuation, something that fits better in some steels and a lot of aluminums, we're looking at a different stress theory, and this is where we introduce distortion energy theorem. This is also called DE, okay? Now again, this very much has to do with the intermolecular bonds and the energy that's stored within those intermolecular bonds. Derivations in the textbook, I am not going to cover the derivation again, even though I think the derivation has value. Using the equation is more important to me. We're going to introduce an idea of the von Mises stress. And this is going to define the stress state at a point, a single point, okay? And when the von Mises stress is large enough, that's when we expect the bond energies in that area to be overwhelmed and the material to fail. Okay, so basic principle. Now, the definition of our von Mises stress is going to be sigma prime. This is going to be equal to sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma 3 minus sigma 1 squared divided by 2, and then we take this to the 1/2 power. The reason why it's divided by 2 is because every one of these stresses shows up twice. Okay, so here's where we have this new stress value, and then this is going to give us our simplest failure condition, which is just sigma prime is equal to Sy over N, where N has the same value. Sy again is the yield strength of material, and this is now our von Mises stress. Okay, if you can have some solver automatically give this to you, this is going to be your fastest way. But oftentimes, again, this is your more conservative. This tends to be faster because you can do that in quick calculator calculations. One calculation, you don't have to plug it into this equation. This is more accurate. This is closer. Your safety factors are going to be more accurate to what the definition of a safety factor is actually supposed to be. Okay, so that's the use of the distortion energy theorem. And now we do have one more ductile failure theorem, and the idea is, what about a material that can handle tension but can't handle compression? Or what about a material that can handle tension and can handle compression? How do we handle failure in those cases? And what this leads to is called the Coulomb-Moore theory. I think it's ductile Coulomb-Moore. Okay, and this is either called CM or DCM. I don't remember which one our textbook uses. But in dealing with ductile Coulomb-Moore theory, the idea is SYT is the tensile strength, tensile yield strength. The Y stands for yield here. And then SYC is the compressive yield strength. And then we're just going to say that SYT not equal to SYC for some materials. Now, it's true that SYC and SYT are going to be different for most materials. But for a lot of materials, it's within an order of magnitude. It may be 1.3, 1.5 times less, one or the other. But when we're referring to this one, we're talking specifically about, like, you may be talking about 10 times less or 5 times less, one value over another, or 5 times greater if you want to look at it glass half full. If we don't have the same, unfortunately, we can't use these theories, because these theories would require us to have one consistent definition for a yield strength. When our one consistent definition for a yield strength isn't just tension or compression, then we have to have something different. Okay, and so in ductile Coulomb-Moore, the equation becomes sigma 1 over SYT. I'm not going to put the negative sign there. Plus sigma 3 over SYC is going to be equal to N1 over N. Okay, so as this value gets closer to 1, as this value gets closer to 1, this value will get closer to 1. Okay, and so that's what we're seeing. Now that's our 3 ductile failure theories. We also have brittle failure. Now when I say brittle failure, it is actually possible for any material to experience brittle failure. If you've ever dropped a piece of plastic, or like a plastic container, and the plastic container just shatters, it's experienced brittle failure. Now plastic itself is called plastic because of its plasticity, but when it just shatters like that, that is brittle failure. We also see that metals that are really cold will experience brittle failure. We're also going to be talking about fatigue and how fatigue leads to brittle failure. But brittle failure, it's not exclusive to one material. So here, the bond energy is going to exceed the intermolecular capacity through loading, causes a crack or hole to propagate through the material, cross section, and this leads ultimately to failure. Now this one is going to rely on SU, not SU-SY, which is the ultimate strength. Okay, so we will have to keep that in mind as well. Now when we're talking about brittle failure, we do have 3 additional methods that we need to consider. So I'm going to go ahead and erase this. Brittle failure, what we've been seeing, some of the qualities that we had. In ductile failure, we were seeing the ridges that were occurring at 45-degree angles. This was not uncommon to see it inside of the material. And so when the material fails, it was evidence that the material was stretched along the shear directions. But when we're dealing with brittle failure, for brittle materials, even ductile materials that are failing in brittle ways, we're seeing a different kind of stress entirely and a different kind of surface. So when brittle materials fail, oftentimes what happens is it is relatively smooth at the actual intersection, which is to say it is failing because the principal stresses themselves are exceeding the maximum capacity of what it's being able to hold. Okay, and so if you think about loading a crack in this way, this causes the crack to pull apart and expand this direction and this direction until you end up with this very nice linear, fairly linear surface. It ends up being really dull too. Brittle failure all tends to have the same appearance. It's not shiny, whereas ductile failure does tend to be shiny. So first brittle failure mechanism is going to be called the maximum normal stress.